Hi everyone. In this video, we're going to consider different types of second derivatives that we can take. And in particular, I mean second derivatives using the del operator. And so using, either taking the gradient, taking the divergence, or taking the curl. Now you might think if we want to take two derivatives, you can imagine every possible combination using these guys, and they should all have their own second derivative. That's not quite right, because remember, you can only take the gradient of a scalar field, whereas you can only take the divergence and the curl of a vector field. So there are going to be rules that, restrain the different types of second derivatives that we could take. So for instance, if you tried to take a gradient of a gradient, that would be not allowed. That's not an allowed mathematical operation. And maybe pause the video here and convince yourself of that if it's not immediately obvious to you why you can't take a gradient of a gradient. So we'll talk about 5 different second derivatives that are allowed. And for the purposes of this video, I want to note, so I'll use t of x, y, and z. So whenever I write a capital T, I'm talking about a scalar field. So it's a function of all 3 coordinates. And then I'll use v as my vector field, which again, therefore, is a function potentially of all 3 of our spatial coordinates. Okay, so what are our 5 different second derivatives that we'll consider in this video? So first, you could imagine taking the divergence of a gradient. I'm just going to abbreviate so that I don't have to write so much. This is actually going to have a special name, which is the Laplacian. And for the purposes of doing physics, this is definitely going to be one of our most important, if not the most important type of second derivative that we're going to want to take. So we want to take the divergence, which is this operator, of a gradient, which is this operator, right? So the divergence, del dot. Again, you can only take the divergence of a vector field. Happily, the gradient of our scalar field t, this is a vector field, right? So this is an allowed thing that we can do. This is often notated as del squared t, right? So that's just a shorthand that's very common. And what actually is this? This is just the second derivative of our scalar field with respect to x, plus the second derivative of our scalar field with respect to y. These are all partial derivatives, note, plus the second partial derivative of our scalar field with respect to z. And that's the Laplacian operation. The second one that we might consider is taking the curl of the gradient. So a curl of a gradient. Again, this is allowed because the gradient turns a scalar field into a vector field, and then you can only take the curl of a vector field. So the curl, del cross something, of a gradient, which is del our scalar field t. All right, it turns out that this is equal to 0 always, which I'm not going to prove in this video. You could definitely look it up or try to prove it to yourself that this is always true. And so, of course, it's not a useful second derivative, really, because it's always equal to 0, but this is going to turn out to be a very useful property. So this is definitely something that you're going to want to remember. All right, what about taking 3, I'll write over here, is the gradient of a divergence. Right, so the divergence, remember, creates a scalar field, and so we can take the gradient of our scalar field. So the gradient, and sorry, these colors probably look very similar, the gradient of a divergence, del dot A. All right, and there's not actually a special, it is what it is. You can calculate it. I'm not going to write out a special identity for it. This guy We don't give it a special name or anything. It doesn't actually come out that often in physics. So it's a second derivative that we can compute, but it's not one that comes up that often. So I'm not going to really spend much time on it. What's our fourth second derivative we could consider? This is the divergence of a curl. So this is del dot del cross V. And this one, again, like number 2, turns out to be equal to 0 always as a mathematical identity. Right? So again, this property actually will end up being quite useful, the fact that this vanishes. So that's one that you want to keep in mind because it'll come up. And then finally, we have the curl of the curl. Which is del cross our vector field V. This, it turns out, is really just a combination of other second derivatives that we have. So in some ways, we don't really think about it as a unique second derivative that we would want to consider. I mean, we could. But so this is really del of the gradient of del dot V, right, which is this guy right here, right? So the first piece is just equal to number 3 minus the Laplacian of a vector field. So I didn't write this over here, but you could also actually take the Laplacian of a vector field, which maybe I will actually add that now. Del squared of a vector field. What do I mean when I write this down? I mean del squared of the x component, x hat, plus del squared of the y component, y hat, plus del squared of the z component, z hat. So that's what this notation means. So this is the Laplacian of a vector field. So that's how we could compute the curl of the curl if we wanted to. But like I said, really, the most important things that you're going to want to remember out of all of these, definitely this Laplacian is going to be very important in physics. And then these two identities where things go to 0, those are also going to be quite useful. All right, so those are second derivatives. You could, of course, go on to third derivatives. We could go on all day. But I think second derivatives are going to be good enough. And for the purposes of physics, second derivatives are going to be most important. All right, thanks for watching.